Hello and welcome to Physics Problems One by One.
So here is a problem. As always, read it, maybe once, maybe twice, and then pause the video and try to solve it yourself.
Today's problem is about bombing. Yes, there is an airplane that flying h high above the ground and it's throwing a bomb. That's how they conducted the Second World War, and basically even after that they do the same thing quite often. Not always they throw a rocket. They throw just a projectile. This is a bomb, and bomb is delivered with speed v0, and this is the speed of the aircraft, because all they do, they open the bottom, and the bomb that flies with the same speed that the aircraft is detached, it starts falling down. And so this is the distance L, and this is h, and this is L, and so the bomb fly like this, and boom, there is explosion. And typically h is very big, like they fly high in the air. They fly 3, 5, 10 kilometers, 20 kilometers, doesn't matter. But we assume that it is h not too big, that we still can decide that g is constant. If they go 20 kilometers and now g is not g, when it's high, it's just a little bit lower. But we assume that something like 3 kilometers, so g is constant. And what's going on? Well, nothing special from the physics point of view. Of course, not very good for the people sitting in this point, but from the physics point of view, along x, the bomb is flying with constant speed v0t. And by the way, the aircraft also is flying with v0t. So at any moment in time, bomb, here is aircraft, here the bomb. Here is the bomb, here is aircraft. So the bomb is always underneath the aircraft, straight below. That's why you actually maybe see some documentaries from the Second World War, and you see the bombs flying and then there is explosions underneath. So the camera was installed on the aircraft pointing straight down and you could see everything. Of course, this negates the air. Of course there is an air. And there, of course, is dragging and stopping. So it's not very precise. Plus there is wind. There may be side winds, there may be this wind. We can estimate how big it should be wind to deflect the bomb from a target. And it's not very much wind should be done because of h. So it's not very precise. But this is how they do it, and they call it carpet bombing, because there are many aircraft flying in the same formation, and they throw and throw those bombs, and this is like a carpet, and it's like with some precision, but there is a lot of damage on the ground. But the point is that let's describe the movement along the y. Along the y, of course, this is h. And by the way, x v0t equal L. And let's put it a little bit differently. X at the moment of time t equal v0t. And this is for aircraft and for the bomb. And y at any moment of time, we already went through this, initial speed in this direction is 0. So this is minus gt squared over 2, right? And so when this thing falls, it's determined by this motion, and this is, of course, instead of x, it would be L, right? And L would be equal v0t, and t is the total time from here to here, and along this, it would be minus h because this coordinate is minus as soon as we put 0 here and y is directed up. So this is distance h, but coordinate is minus h, minus g t squared over 2, right? And we can find anything we want. We can find t equal v0 divided over, oh sorry, L divided over v0, because I'm sending this to the bottom and to another side, and minus minus gone, and h equals L equal v0, and this is h equal, I can put it g, and instead of t I will put this, so it would be L squared divided over v squared, right? v0 squared and 2. So I have h equals this, all right? And so then from here I can find L squared equals 2v0 squared multiplied by h, right, and divided over g. And I can find L equals, and this would be v0, because I extract square from both sides. Let me do it slowly. Square from this side as well. 2v0 squared h divided over g. Square root and gone, so L becomes this. v0 is factored out, and I have square root of 2h over g. And in the problem they ask us how we will see this target. And we will see this target under this angle, alpha. And just from this triangle, we can say that tangent alpha, and that's what they want to find us essentially, is L divided over h. And so we have tangent alpha equal L divided over h, and we have tangent alpha equals, instead of this, sorry, when I was extracting v0 squared, I forgot about this. L over h, tangent alpha equal L over h. Instead of L, I will put this v0, and then there would be square root, and this would be 2 on top, but h would go underneath the square root, and this would be the answer. Tangent alpha equal v0 over this square root. And basically in this problem v0 is given, so you have to substitute it here, and you will get h is given, and basically those are conditions how the pilot see it. The pilot perfectly knows his speed. He is looking on speedometer, I know I'm flying 500 kilometers an hour, fantastic. And he looks on the altimeter and he knows the h. He knows the height. And then he says, oh, okay, when I see this target underneath, under this angle, so he looks down under the angle, and when the angle is this, he knows this when I have to push the button and release it. So basically this formula has a lot of meaning, of practical meaning for the pilots of the Second World War. And basically that's it. This is the same projectile, like an arrow when you use archery, and ball when you play baseball, and a swimmer that jumps from the trampoline, and everything else. As soon as the body is detached and flying with G, the same formulas are applicable, and of course under the same assumptions, that there is no resistance from the air, no drag, no wind, and if those are present, well, conditions will be very, very different. And next problem we will discuss how tolerant it is to the wind. Alright? So if you like this, if you want to hear about next problem, subscribe bell, and questions, comment are welcome. Thank you.